Hello, my name is Saurabh Chaurdia and I am a formal verification engineer with Oski technology. It is my pleasure to present this paper on behalf of the authors from both NVIDIA and Oski. In this presentation, I will be discussing a method to detect circular dependencies in a set of forward progress checkers in a design, which could lead to deadlock conditions being missed in verification. I will start by introducing the concepts of how we define and build for forward progress checkers, how we reason about forward progress checker proof depths, and how decomposition of forward progress checkers can lead to the risk of circular dependencies. Then I will introduce the method that we developed to detect circular dependencies in a set of forward progress checkers. Finally, I will share a couple of case studies about the application of the method to blocks of a GPU level 2 cache design. The issues that we are targeting with the forward progress checkers are deadlock, live lock, and starvation. Deadlock is a condition that occurs when two or more blocks are waiting for each other such that waiting never ends. One example of how this could happen is when each block has consumed some amount of shared resource and there are no free resources left. But all blocks need additional resources to make progress. The dining philosopher's problem is a classic example of this, where the philosophers need two forks to eat, but each philosopher has picked up one fork and is waiting for their neighbor to put one down. Live lock is another type of forward progress issue where multiple blocks are continually repeating the same interaction in response to each other, but none of them can reach their final state. Finally, starvation can happen when a block continually makes requests for resources, but it is never serviced due to being blocked by other priority requests that consume the resources for unreasonably long period of time. A formal checker for deadlock models when the design under test has the ball. For example, when a block has received more input transactions than responding send transaction, then the design has the ball. It is expected to make forward progress and generate an output transaction to pass the ball within a finite amount of time. In practice, there are usually many legal conditions that halt forward progress and which are outside the control of the block under test, such as back pressure on an output interface. These stall conditions must pause our counter so we do not count this time against the block under test. The modeling code for a forward progress checker has a counter that increments for each cycle that the design has the ball. The counter is reset when design passes the ball, and the counter is held at its current value when any stall condition occurs. Then we have an assertion to check that the counter does not exceed the limit of the timeout value. Let's consider the example of memory controller. When the memory controller receives a read request, it must produce a corresponding read response within 16 clock cycles. The has the ball condition is that a read request is pending. The passes the ball condition is that a read response is observed at the output. The timeout value is 16. The memory can apply the back pressure to controller, so that is a stall condition that we would code into our forward progress checker. We can also have other stall conditions such as read after write hazard condition. By using memory back pressure as a stall condition, we are making the implicit assumption that memory will eventually release this back pressure and allow the transaction to flow again from the controller. However, the risk of deadlock is introduced if somehow it is possible for memory to be in a state where it is waiting for input from memory controller before releasing the back pressure. Then A circularity could exist where both blocks are waiting for each other to make progress. Stall conditions such as this become constraints that are embedded within logic of forward progress checkers. The assumption that the stall conditions eventually resolve are not coded as separate constraints and hence cannot be cross-proven on the neighboring blocks. This leads to the potential risk of incompleteness and circularity in proof decomposition. Unless something else is done, system level forward progress bugs can be missed. What to do about this is the subject of the rest of this talk. But before I get to that, one other background topic I want to discuss is the required proof depth for forward progress checkers. An important metric for defining the minimum proof depth of checkers is the depth of witness waveforms of the related cover points. For example, proof depth of a checker for FIFO overflow must at least reach the depth of FIFO full condition. In a similar way, a key cover point for forward progress checker is the point at which the safety counter reaches the maximum allowable value. We require that formal analysis of the forward progress checker reach at least this boundary and explore scenarios beyond this point to find possible failures. In the example of memory controller where the timeout value has 16, if it takes 20 cycles to reach that value, then the bounded proof depth of the checker must be greater than 20 to have confidence in the result. Now let's look at the method to detect circular dependencies. Once we have coded the forward progress checkers for all blocks, say A, B, C and D in a system, we can construct a dependency table which captures the dependencies between blocks. Here the variable A underscore B represents the expression for stall condition that is embedded in the forward progress checker for block A and which is controlled by the inputs from block B. In a similar way, we can capture all the stall conditions of blocks in the table. Now, we can traverse the table to find all possible dependency loops in the system. For example, a dependency loop with potential of circularity is A is dependent, A is stalled due to B, B is stalled due to C, C is stalled due to A. To automate detection of dependency loops, we can code the dependency table in system Verilog using 2D array of reg as shown here. We can then code a circular dependency checker which can be used in formal to exhaustively traverse all the entries in the dependency table and detect all possible loops. It uses undriven wires in the system Verilog code called random variables to allow formal analysis to select all values for the stall block we start with and the next stalling block. The logic of the checker is we start from any random stall block, make it the current block. In the column of current block, We pick any random entry. This selects the next stalling block. The next stalling block becomes the current block, and the selection of the next block is repeated. This is repeated a maximum of total number of blocks times. This defines a candidate dependency loop. Now, there is a potential circularity if a candidate dependency loop, if in the candidate dependency loop, we return to a block from where we started and all traverse entries are non-zero. For such a loop, the hang found signal will be asserted. In practice, we can apply the circular dependency checker in multiple ways. I have listed in this slide 3 steps how the checker can be used. So in the first step, we can replace all stall conditions in the table by 1. In this case, we do not need the RTL of system since we have abstracted it out and replaced all the real stall conditions by a constant. If we get a proof, it means there are no circularities in the stall conditions of the system and we are done. However, more often that is not the case. For a complex design, we will have failures at this step. So the next thing we can do is to run the circular dependency checker on the RTL of the system with the actual expressions for stall conditions in the dependency table. This is the second step. A failure in this step highlights a potential deadlock in the system due to circularities in the stall conditions of the blocks. Now, since the RTL of the system can be very large, it is likely that we can work through the failures. We will achieve an inconclusive result. At this point, we would move to third step and apply abstraction models to reduce complexity and achieve closure with formal analysis on the circular dependency checker. Now let's look at a couple of case studies of how we used this method. We applied the method for detecting circular dependencies to the blocks in GPU L2 cache controller. There are 2 slices of the design, which contain blocks A, B, and C. Each of the blocks has a FIFO at their input interface. Request from block B may require a path to block C in the same L2 slice. Request from block C may require a path to block A of the neighboring L2 slice. We can enumerate the forward progress stall conditions for each of the blocks as follows. Forward progress of A gets stalled when the arbiter grant is with B. Forward progress of B gets stalled when the arbiter grant is with A. One more stall condition for B is forward progress of B gets stalled when it requires access to C and C's FIFO is full. Forward progress of C gets stalled when it requires access to A of other slice and A's FIFO is full. To reduce complexity, we have used an abstraction model which transfers the dependency of C on A within the other slice to A within the same slice, as both slices are identical. By leveraging this symmetry in the design, we can formally verify system level deadlocks using the RTL for only one L2 cache slice. At step 1, when we ran the circular dependency checker on the table without the RTL and a 1 for all stall conditions, we found multiple possible loops. Moving to step 3, we ran the circular dependency checker with the real stall conditions on L2 cache system RTL with abstraction models. This produced a real deadlock failure due to the dependency loops. A is stalled due to B, B is stalled due to C, and C is stalled due to A. In this scenario, A's FIFO is full and cannot accept any more data from C. A cannot drain any entries from its FIFO since the arbiter grant is with block B and B is trying to complete a transfer to block C. C's FIFO is full and it cannot accept any more data from B. C cannot drain any entries from its FIFO since it is waiting for A in the other slice to accept the data. So, none of the requests can make progress and the whole system is deadlocked. After this bug was fixed, we achieved an unbounded proof on the circular dependency checker with the fixed RTL, which provided the utmost confidence in the fix. Here is a second case study where we applied the method for detection of circular dependencies to a GPU L2 cache request coalescer block. In this design, there are 6 virtual channels that are processed in parallel. Virtual channels may receive sticky transactions from crossbar, which cannot be interleaved with any other virtual channel traffic at the arbiter. For these sticky transitions, the entire burst must be serviced before the arbiter moves to next selected virtual channel. Now, if we talk about the global forward progress checker, which is the forward progress checker for entire system of virtual channels. So the cover point for it is hit at a depth of 36 cycles. However, the proof depth achieved for the global forward progress checker is only 35 cycles after a 10 hours run, which is below the minimum threshold. Hence, we decompose this single forward progress checker into per virtual channel forward progress checkers. Since these per VC forward progress checkers contain stall conditions that introduces the risk of circular dependencies going undetected. So we use the method of circular dependency checker. Here is the dependency table for the collection of virtual channels, which captures the stall conditions for each channel, which are: there is a sticky transaction in flight for any other channel, or the channel does not have any L2 flow control credits available. We achieved much better results with the per VC forward progress checker in combination with the circular dependency checker than we did with the global forward progress checker. The per VC forward progress checkers achieved a margin of 9 cycles over the 10 cycle depth of timeout cover point, which is much better than the negative margin that we had for the single global forward progress checker. Also, we achieved a proof depth of 24 cycles on the circular dependency checker with the use of abstraction models, which gave us confidence that we were not missing anything by decomposing the checker on a per VC basis. In conclusion, we have discussed a method for reliably detecting circular dependencies in a set of forward progress checkers with embedded stall conditions. We can use this method to mitigate the risk of circularity when decomposing the forward progress checker, as we did in the case of virtual channels. Also, we can use it to find top-level deadlocks in a system of complex blocks, as we did for the slices of cache controller. That concludes my talk. Thank you very much for watching.